talk that I'm going to give is work that I did on the last year of my PhD at the Max Planck Institute for the Mathematics and the Sciences. Now, it's a very computational neuroscience talk, but the lesson or the idea that I want to somehow bring into this mostly neuromorphic meeting is that basically what was mentioned yesterday, that one can think of spikes as events in time, and that maybe learning is not so much about the weights, but rather about how the time of a spike changes as you get used to a certain input. Now, just to take out of the way a few technicalities, everything that you'll see, simulations, some of the equations that I'm obviously not going to present in the interest of time, they're all based on leak integrated and fire neurons and your standard spike time dependent plasticity. So there's nothing here that is, let's say, outside of your normal play field. The one thing that somehow sometimes creates a bit of confusion is that basically when I have one neuron that gets an input spike train, the input would be random, but it would be fixed across repetition. So if I expose a neuron to a certain sequence of inputs, this sequence is the same, even though up to noise, the timing of the input spikes is the same across repetitions. Anyway, technically it is done. The first or the main phenomena that everything else is based on is the notion of latency reduction. It's a very classical concept. There's this idea. It was in a paper by Sebastian Song and a few colleagues, in which they show that, well, basically, if you have like 5 neurons that fire in chain and they send their spikes to another neuron, then if this other neuron generates a postsynaptic spike, this postsynaptic spike would advance as it learns. Basically, would happen earlier and earlier because it potentiates inputs that come before, therefore, they will generate a spike earlier. You can obviously extend this to very simple, like uniform inputs. But there's a couple of things to be careful with. One is that if you have your theoretically nice, perfectly antisymmetric stdp, where basically the depression exactly compensates potentiation, in this setting of sparse activity and spikes moving forward, you're going to generate more postsynaptic spikes. Conceptually, this is basically because if your postsynaptic spikes moves forward in time and it doesn't change anything on the input spike train as it passes, eventually it would be very far away in time, and then the presynaptic spike train is left unchanged, so it will generate the same spike that was there at the beginning. So yeah, basically to prevent some sort of instability due to learning, you have to make sure that the depression is somehow slightly larger than the potentiation. Yeah. Another thing to mention is that if you have, let's say, 2 postsynaptic spikes and they all advance in time, then then there will be a point where you will reach the beginning of your input, so the beginning of time, if you will, and then the second postsynaptic spike is somehow weaker, or it's in a disadvantageous position with respect to the first. Now, if there's no noise, you will just have the 2 spikes that would somehow get close together. But if you do have some form of noise, if the first postsynaptic spike disappears, nothing will change, because basically the second postsynaptic spike also reinforces the first. So it reinforces the inputs that generate the first. Whereas if the second postsynaptic spike disappears, the first postsynaptic spike weakens every input that led to it. Therefore, it automatically basically cancels it. Incidentally, this is some sort of phenomena that led eventually to the discovery or the study of triplet rules, but that's somehow just a side technicality. Anyway, so what I've been talking about so far, it's on how individual spikes change. But the interesting case is obviously not when you have a single spike, but rather when you have many of them. And then you have to have a bunch of constraints to make sure that this independence is maintained. They're nothing too complicated. I'm not going to get into the details because basically I don't have that much time. And it's also not that interesting. But basically, you need to have a certain number of spikes that have to come from different neurons. So you cannot have few neurons that spike all the time. You must have basically you must have some sort of sparsity in the activity of the neurons at every point in time, and every neuron cannot be active too often. You can also add inhibitory excitatory balance. All the simulations that are from here on include that. It's not necessary, but it's somehow useful for, for at least from computational neuroscience, it's quite relevant nowadays. And even though everything is based on this stdp rule that I mentioned before, you get similar result if you try cliplet rules, or if you change the inhibitory kernel, or basically, these results are generally fairly robust as long as you have this notion of stability and this notion of independence of the evolution of spikes. Okay, so now we have a postsynaptic spike train, and we want to see how it evolves in time. In time, meaning that every time I expose my neurons to the same sequence, what happens to my spike train? Well, the natural way to do that is to look at the interspike interval, and then you can look at the cumulative probability distribution of this. So basically what will happen is that the first postsynaptic spike would move forward, as because of this latency reduction phenomena. And the second, third, so basically the subsequent spikes would spread apart. That's because anytime like a postsynaptic spike gets too close to the presynaptic, to an earlier postsynaptic spike, it disappears. So there's some sort of repulsion that happens in that scale. Now, this is basically just how to visualize this, but actually what ends up happening is that your postsynaptic spike train concentrates all the basically if you have a population of neurons that gets an input spike train, each neuron getting its own different input, you will get a peak of activity at the beginning of your sequence. So the first postsynaptic spikes would concentrate in a relatively small window, and the others would spread apart. And by spreading apart, they would actually reduce the number of postsynaptic spikes. So if you're thinking in terms of coding performance, you can think, well, this peak of activity is easier to decode if you have a readout that has finite memory. And the fact that you have less postsynaptic spikes somehow implies that you end up having a lower metabolic cost for input sequences that you're used to. Incidentally, this phenomenon also gives you predictions. So if your postsynaptic spikes advance in time, that they might end up firing before the stimulus that they originally encode. So think, for instance, if you're listening to your favorite tune, and this tune has three populations of neurons that are activated in a sequence in such tune. The neurons that react to the second tone in this repeated sequence basically fire after receiving spikes from the first population, so they start firing earlier, and therefore they start predicting their own firing, if you will. And the somehow nice thing here is that for this to happen, for this prediction to happen across, let's say, this simulation is a stimulus that overall lasts 1.5 seconds, the neurons can actually have very short time scales. So even if your chips are in the order of, let's say, 5 milliseconds, or even if all the learning and all the neuron timescales are very short, you can still get predictions that are orders of magnitude larger. Yeah, and that's pretty much everything. Basically, there's this latency reduction, which is actually quite an interesting phenomena that it generates a peak of activity when you present a known sequence, and reduces the total number of spikes. And incidentally, this is the same mechanism that makes predictions emerge. Now, there's a couple of things that are somehow nice from this. One is pure theory on efficiency of sparse codes, but the somehow more neuroscience evoked questions is that, first of all, if you have a mechanism that basically creates good codes, and if this mechanism happens to also give you, let's say, higher order functions such as predictions, it's not too far-fetched to think, that maybe this is how we end up learning to predict. By basically trying to have more efficient codes, we end up getting predictions, which resonates fairly well with people in information theory. Another thing that I found somehow interesting is that most of the time when I present this, the idea of predictive coding always comes along. This notion that, you know, you'd have like a scheme in which like a population has like different layers, and upper layers give predictions to the lower ones. And this somehow tells you that you, at least in the temporal domain, you don't need the upper layers. You can just let neurons self-organize and do predictions by their own. Anyway, that's pretty much all. I would like to thank my collaborators, Masoud and Jürgen, with whom I worked at the Max Planck Institute for Mathematics and the Sciences, and the founding, which I got through the Max Planck School of Condition by the Bundesministerium für Bildung und Forschung. Thank you very much, and I'm happy to take questions.